Okay, so we'll start. Good afternoon, everyone. I hope you are all safe in your homes. And I would like to thank you all for joining us today in this series of quantum matter seminars, which is organized by Professor Adrian Fagin from the Northeastern University. Just some announcements. If this is the first time you are joining us, be very welcome and check out the next talks we are going to have in our agenda on your website. If you would like to watch the recordings of the previous videos, you can do so by going to your YouTube channel on the Matter Seminars EU. We have all them available for you to watch as you like. And I think that's everything for before we get started. Today we have the pleasure to receive Professor Eun-ah from Cornell, and she's going to talk about machine learning of quantum emergency. Just some instructions during her talk. She will give us some time for questions, so you can either raise your hand or type your question in the chat box, then we will read it for you. Thank you very much, Eun-ah, for being with us today, for accepting our invitation. Now you can get started. Thank you.
Well, thank you. It's a great pleasure to be giving this talk. And I would like to really thank the organizers for doing great service to the community. I want to tell you about interpretable machine learning for quantum emergence. And specifically, I will be talking about the results that you can find in this preprint, where we've been analyzing voluminous high volume X-ray data. And this is unpublished, not even on the archive, but work that I'm really excited about, where we're using ideas of correlation functions to develop a interpretable machine learning algorithm. So before we go into why we want to use machine learning and how we use it, I want to step back and think about what the community has been trying to do. So this is an example of a material, cadmium rhenium oxide. It's got a large unit cell. It's a pyrochlore material. It's a pyrochlore superconductor. But this is just an example. But if you think about a material like this, when you just reduce it down to the formula, which atoms, how many of them are involved, that does not look like a whole lot of information. But if you start to ask questions about defects, if you start asking questions about density distribution of electrons, orbitals, quickly the content, the volume of information in materials grow rapidly. So, you can have many terabytes of data that, or the information content can easily grow to be a terabyte of data or several terabytes of data, which is, more than the content of information in the Library of Congress. And knowing that because the degrees of freedom are so small, so knowing that there is humongous amount of information that we would like to get out, the community has been putting a lot of effort when we try to figure out how do we understand and control what different structures mean for the material properties, such as soot versus diamond or high TC superconductor. We want to understand, we want to control, we want to figure out the information that is locked inside the material. And the pursuit for that information have led to experimental efforts trying to get more and more of that information out using different types of probes or using more comprehensive techniques, developing the detector technology, developing new kinds of measurements. And what we are facing today, in a way, is data-driven challenges. So what do I mean by data-driven challenges? Let me give you an example. So X-ray experiments, X-ray diffraction in 1913. This is a famous paper from Bragg and Bragg, father and son, in Proceedings of Royal Society, where they, for the first time, explained their hypothesis how to interpret, how to analyze the X-ray scattering data. This is a single cut, and this is an intensity plot as a function of angle as they crank the sample by hand. And what they did first was what we call forward modeling. They said, okay, if there are atoms and if they are arranged in this regular fashion, then we can model what X-ray would do. It will reflect like this and there will be interference. And from that, we can infer that what the lattice spacing is. And this is an example of a successful forward modeling. It was so successful that we teach this as introductory physics material. However, 100 years later, more than 100 years later today, still the modality of X-ray analysis, X-ray diffraction data analysis is relying on forward modeling because we cannot retain phase. The information of phase is lost when the photon is counted. We just have the intensity, we don't have the phase information. So we cannot completely invert it. So we rely on forward modeling. But forward modeling becomes more and more difficult. Now we come to the modern facilities. Let's see if I can run this video. Always have difficulty trying to run. Somehow, okay, I'm not figuring out how to run the video, but the video is just showing how, you know, when you rotate the sample, this is the angle phi, the cut of the Brillouin zone, you are just going over this whole space and you're cutting through many, many Brillouin zones. You know, these are specific numbers from the Argonne National Lab. So you acquire terabytes of data in a matter of an hour. This is large volume of data that have enormous amount of details that, you know, much larger fraction of the information content that we manage to retain. However, this volume escapes our ability to rely entirely on forward modeling. So that's an example of data-driven challenges. So what my group has been doing over the last couple of years is trying to meet these data-driven challenges in different types of experiment or even computational experiment, computational simulation data. And so for instance, we looked at scanning tunneling spectroscopy data in this paper. We looked at resonant ultrasound spectroscopy. This is another example of where, you know, the structure of the data, this is a case where the data volume itself is not big, but it's not easy to model. And you want to learn what's inherent in the data. So generally, we are looking at data sets where the structure is either complex or big. This is an example of scanning tunnel transmission electron microscopy data where the data structure is 4-dimensional. And this is an example of data from quantum systems, trying to do tomography using natural language processing algorithms. And this is looking at non-Fermi liquid transport in quantum Monte Carlo simulation data. So in all of these, our approach has generally been that we would like to learn from the data, and we want to get from data to understanding some simple principles. And but with the data structure being complex or being large, having more information than we are used to having in our textbooks, when the path is not immediately obvious, we can use data science tools to make that bridge. And my approach to using machine learning is that really that it is a tool. Now, what I'm showing you here is an example of a wonderful tool. It's a commercial grade blender. If you're after making, you know, smoothie quickly for a large crowd, this might be your tool. However, if you're after making an authentic guacamole, you don't want to use a tool like this, but instead you want to use a tool like this, which is kind of, you know, what looks like a Stone Age tool. but it's the right tool for the task of making authentic guacamole in which you can see what went in and how the flavor is blending. For the same reason, what I always recommend is look at the problem at hand, whether you're trying to make smoothie or whether you're trying to make guacamole, and try to find the minimal kind of tool that you need, because ultimately what we are trying to do is to make contribution to the progress in physics. And physics is a subject with long tradition and very rigorous structure of thinking. And we have to bring it back to whatever we learn from data has to be something that we can bring it back to our thought process, our infrastructure of thinking. And that requires being able to interpret. And when you have blended everything in a using most powerful machine off the shelf, you may not be able to interpret what went in there. But if you use something that is lower key with just a minimal ingredient, and if you can interpret what is being learned, then you can actually contribute to the progress. So that's my position on how we can make progress. Try to use minimalistic approaches. Okay, so the first part, I want to talk about our unsupervised machine learning for voluminous X-ray diffraction data. And in this paper on the archive, we presented the tool that we worked on developing, polishing, and applying over the course of last 2 years. And the tool we have dubbed it X-Tech, where X is for X-ray and TE is for temperature. So we're looking at temperature dependencies and clustering based on temperature dependencies. This was spearheaded by my former student, Jordan Vanderlee. He single-handedly made the initial breakthrough in making the algorithm work over the course of summer 2 years ago. And Mike Meddy then together with Jordan developed the code into what is usable now, and they've applied it to many different data sets. And we had a pleasure of working together with colleagues in computer science, my colleague Killian Weinberger and his student Jeff Pleiss. It's been really fun to try to communicate really across different disciplines, talking to people who do not know what momentum is, and not to mention crystal momentum, describing how we want to learn correlation between different Brillouin zones. The key idea came from discussions with Jacob Ruff at Chess, and we have had really fun collaborating with Matt Croxted and Ray Osborne and collaborators at Argonne, where we got to really look at the data that nobody looked at before. So what are we trying to do? When we try to detect subtle ordering or fluctuation phenomena, we're trying to look for special region in the reciprocal space. This is three-dimensional reciprocal space with intensity shown, where we're showing 20 by 20 by 20. That's 8,000 Brillouin zones. And sorting through that, trying to find a special special set of cues associated with ordering or fluctuation is a little bit like sorting through a way too big a pile of Lego when you're a kid, if you have kid or a niece or nephew comes to you and say, I need this special piece to make this, project of mine from the manual. And I've spent way too much time trying to meet those requests. And it took me no time to learn what is not a good approach. What is not a good approach is to try to pick one piece at a time and look at it and inspect, is this what I'm looking for? Is this what I'm looking for? That's definitely not a good approach. However, making a sort of judiciously chosen cut and trying to see, am I finding something interesting? is sort of that kind of an approach. So that's kind of a manual approach that's not very efficient, and it's tiring. It's very easy to miss interesting things because we cannot, stay focused. What I quickly learned to be a good approach is to sort. And with Lego set, there are some obvious choices. You can sort by color, you can sort by shape. These are two kind of obvious choices. And if I'm looking for a piece that has a specific color and a specific shape, by sorting two different colors, sorting by color, what I have accomplished is narrowing down what is it that I have to look at. I can now just focus on to that bin that has the right color that I'm looking for. Now the problem is one would like to develop this kind of sorting scheme, some logical scheme, but with unlike Lego sets with X-ray data, it wasn't immediately obvious that what we should be using as a scheme. We cannot just go by intensities, because highest intensities are coming from the lattice constant, lattice peaks, and those may not be what we're after. So when you cannot just rely on the raw number, how do we go about finding what's interesting? And that's when we start to think about, okay, so what are we interested in trying to find? What are we interested in trying to learn? The collective phenomena it boils down to this, famous simple equation. One would say this is just thermodynamics, but I am starting from statistical mechanics perspective. From statistical mechanics perspective, what this says is that this is Helmholtz free energy, the log of the partition function, has to do with the Hamiltonian, or energy, which has all the information about the interactions inherent in the system. And there is a balance against entropy, which is driven by temperature. So if I'm interested in some collective phenomena that's driven by energy, yes, maybe I'm interested in zero temperature behavior, but what I'm really interested in is what gets picked up or how things change when temperature changes. So we expect different clusters of temperature series among populations of momentum. And if we look at the intensity as at each point in Q, and if we just observe intensity at each point in Q, because that's what's recorded as the temperature changes, and we can look at it in a comprehensive way, because I'm not trying to do it manually, I will have my machine do it. We'll be able to discover where in different points in Q space something non-trivial is happening when changes through the change in temperature dependence. And the approach we're taking, the gist of the idea came from sort of a casual conversation I had with Killian when I was explaining to him, like, I want to track, we have this control parameter called temperature. When we change temperature, some things go up and some things go down, and I want to be able to use that as a guide. And he said, well, that maybe kind of sounds like trying to verify speakers. If you have multiple people speaking and if you record their audio all collectively, you would have the whole signal looking like this. But if you learn that there are, by trying to sort out the existence of different speakers in this soundtrack, we can kind of actually sort out one speaker and another speaker, here marked as red and blue, based on their kind of qualitative features, without necessarily trying to model how peak is going up and down, but by just looking for different qualitative features. So similar idea is what we're going to use to the X-ray data. Now we're going to treat the temperature dependence, the temperature series, like the time series of the audio signal. Now the entire data set, this is a slice of titanium diselenide data. Entire data set is has intensities at all points in Q space, but information content is really concentrated around some peak locations and the vicinity of peaks. So it's kind of a sparse data set. So we go through a pre-processing that step that cuts out the background noise and allow us just focus on where there might be some meaningful fluctuations and meaningful intensities. And what that does is taking the raw temperature series. This is plotting intensity from every point in Q space, the reciprocal space points where data exists, as a function of temperature in a single plot. So it looks like a huge mess. Once you threshold and rescale so that you can look at the Bragg peaks that have scales that are, orders of magnitude, several orders of magnitude higher in intensity next to the diffuse peaks together, one can get something looking like this. And even now, by eye, this is pretty messy and it's kind of hard to tell what is going on. But this is the first step. The thresholding and rescaling is the first step. And this kind of reduced space and reduced data set is what we're going to now work with. So what we do with now, select points in Q space that's passing the threshold scheme, and their temperature series associated with each of those Q points, is to use what's called Gaussian Mixture Model. So Gaussian Mixture Model says that it's modeling the data distribution as having to do with multivariate normal distributions. And this number K is the number of clusters that we choose. Sometimes we work with 2, 3, and this is the only parameter that we set. And what we typically do is try varying this parameter to find what is a natural, actually inherent to the data set parameter. But once you set that K, the number of clusters, what you're doing is you're modeling the distribution of the data. This is a probability distribution as coming from normal distribution associated with some mean and some variance. Now this mean, because this I tilde of Q is this whole series with the whole temperature trajectory. So if I had D to the T, let's say 30 different temperatures, there will be 30 different intensity at each of temperatures in here. And I'm modeling it as a Gaussian distribution or normal distribution in that 30-dimensional space. So I have my mean, that is the 30-dimensional vector here, and the variance, but this is just a Gaussian distribution. And I am assuming there are K different distributions. And this pi of K is the weight. So for each Q point, we're trying to learn what is its cluster assignment for a given point. It would have a cluster assignment to belong to a cluster K, which is set by this weight, pi of K, and the strength of the distribution at that point. And we learn these parameters, pi of K, M of K, and S of K, this mean, variance, and the weights by optimizing. So, So we learn this by optimizing the probability distribution to maximally the best capture the actual distribution. And that process is kind of like doing mean field theory. You're trying to best capture you're trying to optimize the distribution fit to the actual data set. So once you have the mean and variance, you have the cluster assignment and cluster assignment for the data to belong to a particular cluster, that's the result of the analysis. Now, this sounds rather abstract, so let me try to demonstrate it with a data set. So the material that I'm going to focus on here is a pyrochlore superconductor cadmium rhenium oxide. It is known to have at least one very well-defined structural transition that is a continuous transition. And there is possibly a first-order transition around 110 Kelvin, 113 Kelvin. There have been some proposals about what kind of structures the system is in, what the structure is in. But this transition at TS1 have been debated since this nonlinear optics data experiment inferring that transition at this point. From the structural point of view, it's been conjectured that this might be the structure that you're lowering down to. But that transition, which would have been an E order parameter, this paper claimed cannot be a primary order parameter. So since then, there has been a lot of debate. And in general, what is going on at this transition or that transition have not been entirely known. And although there have been some conjectures about what could be the lower symmetry phase, knowing the structure well at high temperatures, the displacements are extremely small. The distortions are really small. And it's been hard to really pinpoint. And there have been no knowledge of what's happening inside each of the unit cells. So we took about 8 terabytes of data and clustered. And this is the result of clustering, assuming the region near each Bragg peak to belong to the same cluster. That is, we assume the region near each Bragg peak to be correlated. The transitions are not associated with any period doubling, so this is not a charge density wave system, but this is more of a intra-unit cell change. The unit cell size is not changing, but the symmetry is changing. And when we assumed 2 clusters, this is the result we got. And you can immediately see that what's being plotted here, the solid line is the cluster mean, and the shading around it is the variance. So you can see that there is a very tight cluster that's not showing a big change. And there is another cluster that is showing a big change at the upper transition. Now, this clustering is done without any knowledge. The algorithm has no knowledge of anything other than the fact that we told the algorithm to look for 2 clusters. And we told it to look at the temperature dependence. Now, once we have this clustering result, we can, because we know for each of the Q points in the reciprocal space, we have this assignment, we can look at where they are. And that immediately gives us interpretation. So when we look at where the purple points came from, these are the Q points where the purple points came from, and these are the points where the yellow points came from. And this is not the data, but this is where the map of where the clusters are coming from. And we can see that, oh, the purple points are the positions where Bragg peaks or symmetry disallowed. They were not allowed by symmetry in the high temperature tetragonal phase. But upon the lowering of the symmetry, they now become allowed. And the fact that we're here for visibility, I am showing one slice, one particular slice and a small subset of the data. But we've seen this in over 10,000 Brillouin zones, and every single point it works out. So we've analyzed 10,000 Brillouin zones volume of data. We are absolutely sure we didn't leave out anything. Now, once we did that, we wanted to know a little more. We wanted to see whether there is something that we can learn from diffuse scattering. there is any fluctuation that we can learn about. So now we didn't let the whole region near the Bragg peak to be treated as one, but we just let each Q point be treated separately. And when we did that, when we looked inside the Bragg peaks, what we found is, it's kind of hard to see from this, but if I blow up, this is the result of 4-cluster clustering. So there is this black, and this black, which is showing relatively weaker temperature dependence, well below the 200 Kelvin upper transition, turns out to be associated with the centers of all these peaks. So the centers are not showing a huge temperature dependence once you are well below that upper transition. However, what is showing a much more pronounced temperature dependence is the diffuse region around these Bragg peaks. And there are diffuse region around the Bragg peaks which have generally higher intensity in this so-called phase 2. And then there are regions which have lower intensity that picks up. And from looking at these points, this clustering results, we could then confirm that that's indeed going on by looking at the raw data. So we go to those Q points and make a cut. This is making a cut, and vertical axis is temperature, and horizontal axis is the Q, and the color scale is the intensity. So what we are seeing here is that for some of these Q points, we learned a clear selection rule, and for some of those Q points, we could find there being a extended diffuse scattering happening over a pretty wide range, all over the entire phase. So this is not a critical scattering. This is not a critical fluctuation. It was fluctuation that's sustained. This is a fluctuation that's sustained inside the whole phase. And we were really puzzled at the beginning. For me, I'm not an X-ray expert, so I didn't even know to be puzzled. I didn't know how to think about it, but I didn't know to be puzzled. But my X-ray expert colleagues at Oregon National Lab were really puzzled. Like, they've never seen something like this. You might see critical scattering, but this is happening over the whole phase. What we later learned by looking deeper into this was that this is actually consistent with Goldstone mode. So the order parameter associated with the transition, which we could confirm already by looking at where this onset behavior is coming from, we could confirm the order parameter has EU symmetry from the selection rule there. But then if it has EU symmetry, which is a two-dimensional representation, it would have a Goldstone mode. And what this is showing is that consistent with Goldstone mode fluctuation as earlier evidence from Raman scattering. But moreover, it wasn't happening in all Qs. It was happening from the selection rule. We could learn that, oh, this is happening when there is a Z direction displacement, Z direction fluctuation between that's in opposite direction, out of sync between cadmium and rhenium. There was a very detailed microscopic atomic scale information that we were able to get by being able to look at the whole data set from a very different angle. Now, this is the first time X-ray data was able to confirm something about Goldstone mode fluctuation. And this with this very subtle, small changes that we were able to pull this out. This was really possible because we could take statistics over a large number of Brillouin zones, and we could gain confidence because we could confirm this in this large volume data. And I believe this approach of looking at the data and clustering based on temperature dependence is something that can be applied not just to X-ray, but for other types of experiments as well. And I'm really excited about how the prospect of this being able to aid discovery sort of in a real time. Now I am about to start switch gear and change the topic slightly to a different type of problem, which is a real space image-like data. At this point, if you have any questions, maybe this is a good time to have a small break for questions. Any questions?
Anyone who have questions can raise their hand or type it into the chat box. I think we don't have any questions, so
All right.
we can continue. Thank you.
Okay. All right. So now switching gears to image-like data. So here we're proposing what we are dubbing correlation CNN or CCNN for quantum images. And why we call it correlation is going to become clearer as I discuss. This was in collaboration with colleagues at Harvard, with Eugene and Annabelle, and again with Killian and his student. And this was really led by my beginning graduate student, Cole, who's just blowing me away as a first-year graduate student who's already nearly completed really impressive work. So what are we trying to do? We're trying to learn what's going on in image-like data, specifically quantum gas microscopy. But again, I believe the approach here will be applicable beyond quantum gas microscopy. The quantum gas microscopy is a technique which have really moved the exploration of ultra-cold atoms forward. And this is when your ultra-cold atom systems trying to simulate the quantum matter, for instance, like Hubbard model, by being able to image and know their state of these atoms, you're getting a snapshot and trying to figure out what state would the system would like to have. And this is the kind of the setup where this is done. And what you're ending up with is images like this. When I first showed one of these images to Killian, he said, well, that kind of looks like a Go board, black and white, and that's nice and simple. Should be able to figure out what one can learn from it. And that's how we got started. So the model that's being simulated here is the Fermi-Hubbard model. That's being considered the minimal model for cuprate, and there's all the questions about what happens outside of antiferromagnetic order and T-wave superconductor in the pseudogap region. The current data set experimental data set that we have access to only can tell us one species of spin. So this black and white Go board pattern tells us whether there is spin up or there is no spin up. So white here could be spin down or it could be whole. So the information content in the measurement is not quite complete. As you dope it away from the antiferromagnetic order, you like to figure out what is going on. And antiferromagnetic order is an obvious pattern that you can try to look for, but the states outside of the order state are kind of states that are not quite so obvious to tell apart. So the two theories that we try to differentiate here is the idea of geometric string that Eugene and collaborators proposed, and pi flux theory, for instance, starting from RVB picture. And they have very different physics underneath them. But when you look at the kind of snapshots that you would get from them, it's not really obvious what you can look for. So this is an example of hole propagating from the geometric string picture, where this whole propagation of this green hole has left a string behind it. And that string has to do with these ferromagnetic bonds. And again, there are these ferromagnetic bonds coming from this string. And the pi flux theory is this superposition of RBB, the singlets being disrupted by the existence of holes. So conventional approach is to look at magnetization or two-side correlation, but neither of those tell apart these two theories all that well. If you try to use off-the-shelf CNN, that's convolutional neural network from, say, TensorFlow, convolutional neural networks have deep neural networks have enormous number of parameters, and often they're over-parameterized, but most importantly, they're black boxes. So, if you give an image and it's going to say, well, this looks like geometric string, this looks like pi flux, but you don't know what its criteria is. You don't know what it is calling the shots based on. So what we're proposing is correlation CNN, CCNN, which is a kind of adapted version of convolutional neural network, where we do have a convolutional layer. So this is, you have some filters, some number of filters, and you can form a convolution. But we don't just stop there. We need to have nonlinearity, but we don't want to have arbitrary nonlinearity, which is hard to interpret. So what we do is we take the convolution layer, we look at derived convolution that is amounting to looking at a second order, higher order polynomials of that same convolution, and collect all of those together to go through a logistic regression step, which is making the decision, firing the shots. So this is sort of the architecture, and the correlation filters are all deriving from a single set of filters, this one set of filters. So we will learn one set of filters, which go into a whole cascade of correlation filters. And then we'll be able to later look at which filter at what level of correlation was triggered for calling the shots. And in order to figure out which filters, which layer, which level, what order of correlations mattered, what we do is this regularization path analysis, where there is this penalty for turning on a particular filter, in this case, this correlation filter. And when the correlation filter is turned on, when upon lowering of the penalty, if the assessment accuracy goes up, like here is a jump, that tells us turning on of this particular filter was important. So using the regularization path analysis is not an uncommon thing. It is one of the ways of people trying to interpret what's going on. But when you just use a regularization path with the conventional CNN, you still cannot interpret those filters because they go through the whole nonlinearity. But in our case, we are looking at specific order of a particular filter. And what we've learned is that for the geometric string versus pi flux, what seemed to really matter is the fourth order correlator. Now those were the first ones to be turned on and leading to a large bump in the accuracy. Now, because we know exactly how these filters were made, we can try to interpret. So what do we mean by fourth order correlation? Fourth order correlation means that we have three channels, spin up, spin down, and hole. Fourth order correlation means it's 4 pixels together are forming an important motif. So now we can go around, find 4 pixels from a particular region of our filter. This is a 3x3 filter in 3 channels. So for instance, these two have high intensities. So if I pick these 4 pixels and go to each of the channel, those 4 pixels, those 4 pixels, those 4 pixels give me either this pattern or it can give me this pattern, as if because this hole is pretty strong. So by just looking at the fact that the fourth order correlator mattered, we can figure out, okay, so it's this collection, not just 1 pixel by itself, not 2 pixels, but it's 4 pixels together are forming something meaningful. So this allows us to give physical meanings to the filters that were learned. These were the filters that were learned in the context of this architecture. And from the filters that were learned, we could figure out, okay, so these are the motifs. These are the motifs. And now we can see whether they actually make physical sense and if they are really in the, whether it makes sense for them to be discriminating features. So now if we go back to the geometric string, so the top is the filter associated with geometric string, bottom is the filter associated with pi flux. We're just trying to tell apart these two theories. For the geometric string, we see that the whole wake that this hole leaves behind has 4 pixel patterns. That's, for instance, this is a 4 pixel pattern that looks exactly like this motif. This is a 4 pixel pattern that looks like a mirror image of this motif. And then these are the 4 pixel patterns that looks like a rotated image of this motif. So we could, once we went through this process, we could realize, oh, the fourth order correlations would be able to distinguish these two patterns. And then we could actually just go into the data and start counting, like, do I really see these kind of motifs? And indeed, those are what we are seeing. And what we are really excited about this whole approach is that the architecture that we're proposing here. Let's see if I can, yes. So this architecture, which is, okay, if you give me, it does not have to be 3 channel. This happens to be 3 channel, spin up, spin down, and hole. But you have some image-like data. That could be quantum gas microscopy. That could be any other kind of imaging probe. Could be STM. You have image-like data. And you're trying to look at it with, you're trying to learn meaningful motifs in it, patterns in it. And this architecture not only can learn what it judges to be a characteristic, meaningful, discernible features, but we can look at what it's learned, and we can decide whether we believe that to be was a meaningful exercise. And this was actually very important because when we try to compare the simulated data to the experimental data, we were able to figure out what the distinction between the simulated data and the experimental data that the neural network the CCNN was picking up on was not the information that we hoped it would look for, but it was actually looking at first order correlation, which is just the net magnetization. there was the assessment of net magnetization on the experimental data was slightly off, and that's all it was looking for. So this kind of mode of hypothesis testing, that is comparing the using neural network trained on simulated data to analyze or draw conclusions about experimental data. This is increasingly becoming a popular approach, because for scientific data, often we don't have redundancies. We don't have repeat of same experiment to build a training set. So for supervised learning, which this is an example of, often we try to use simulated data to train because that's cheaper. When the simulation is not all aspects of the real data, but some salient aspects of it, and try to apply that neural network to the real experimental data. And if we don't, when we don't know what the judgment is being based on, it can be, you know, totally off. So this was kind of a cautionary tale, but also I think it's really the right kind of approach, that we want to look at our image-like data while having control over what the judgment is based on. So with that, I think I'm staying very much in time. Let me conclude. I talked about two different things that are kind of recent that I'm really excited about right now. One is unsupervised and actually very simple approach for large volume diffraction data, the X-TEC, where we use the fundamental role temperature plays in to discover the regions in Q space that are active for ordering or even fluctuation. And the other was correlation convolution neural network, where we're proposing sort of interpretable machine learning approach that is taking advantage of the fact that the data set that we are trying to analyze, the image-like data, still are much simpler than image of cats and dogs and zebras. But moreover, we're looking for different things. We're not looking for taking the criteria for calling a shot between, say, geometric string versus pi flux is very different from calling the criteria for cat versus dog. And if we probably necessarily do not need the deepest, most complex neural network, because going with the complexity and expressibility of your machine learning algorithm, you know, the price you pay other than having to learn all those parameters is big price you pay is lack of interpretability. So again, we're trying to do minimal level of sophistication in the neural network, but trying to, you know, maintain control over being able to interpret. And both of these approaches, I am confident can be applied to other specific data formats. And I think this kind of approaches for looking at the data-driven challenges in the quantum matter world from the vantage point of making use of data science tools, but staying very true to, you know, what's scientifically important for us, can actually lead to meaningful progresses. So with that, I would be happy to take questions, and thank you for your attention.
Thank you for your talk. Questions? There's a question by Deepak. You are able to unmute yourself.
Hi, Eun-ah. I'm sorry, I don't exactly have the right pronunciation of your name, I think.
You got it right.
Did I?
Yeah.
More of a terminology, I guess, question. When you were talking about X-Tech, you mentioned there is a certain symmetry associated with the Goldstone mode.
Yeah.
This Pyrochlore lattice.
Yeah.
What is that? What is that symmetry, and why is it associated with the Goldstone mode?
Oh, so the Goldstone mode requires order parameter to be continuous, and the order parameter here. So the fact that we detect Goldstone mode is a strong evidence of the nature of the order parameter that we've inferred. So the order parameter has EU symmetry, which is a two-dimensional representation. So two-dimensional order parameter means like XY model, you have a Mexican hat potential situation.
Right.
And if you have a, if you have double well potential, there's no Goldstone mode. That's one-dimensional representation, Ising model. Double well does not have a Goldstone mode, but if you have a Mexican hat, which is going around, you have a Goldstone mode associated with going around, right? So the fact that we see this diffuse scattering, the reason why we think it's Goldstone mode is because we see this diffuse scattering over the entire phase, not near the critical point. It's just in the whole phase. It's something that's absent before you order. It's only present in the order phase. Now, the selection rule that had to do with where we see the Goldstone mode, and there was also the further analysis of looking at the average intensities, was that somehow the Goldstone mode was more visible when for the Q space points that have to do with the C-axis fluctuation, C-axis distortion. So this is order phase. You have to first distort, and around that your distorted position, you can have fluctuation, and the distortions, which particular way the distortions are happening, had not been known before. And now we know the distortions are happening with cadmium and rhenium distorting in the C-axis direction out of sync. In a tetragonal phase, there is no notion of C-axis because all direction is the same. But this is in the high symmetry cubic phase. So now in the low symmetry phase, there is a distinction between A, B, and C. And what we've learned by looking at where we see this fluctuation and where we don't, where we see the fluctuation is where the distortion is happening. And the distortions, we could track it down to having primarily to do with the Z distortion of cadmium and rhenium being in the opposite direction. And I think it's kind of hard for me to explain in further detail, but it's detailed in the paper. You can look at the preprint.
Okay, sure. No, thanks a lot. Thanks for a very nice talk.
Thank you.
Any other question? I think we don't have more questions. So thank you, Eun-ah,
All right.
again.
Thank you.